Okay, another distance difference between ionic formulas and covalent formulas is that within ionic compounds, there's only one combination of atoms that can exist, or only one ratio that can exist between atoms in an ionic compound. All right, this isn't entirely true, and we'll talk about why that is in just a little bit. But for right now, why are we making this claim? All right, so remember what has to be true about an ionic compound is that the ions have to combine in a ratio that overall gives us a neutral compound. All right, and we know that sodium tends to make a +1 ion and chloride tends to make a -1 ion. All right, and so if you were to say, well, why can't we have a compound which is NaCl2? All right, well, you can explain that by just showing the ions. All right, sodium makes a +1 ion, chloride makes -1 ions, and if we were to show this overall arrangement right here, that would not be a neutral compound. So again, this combination right here is not neutral, so therefore there is no such thing as NaCl2. All right, this combination right here doesn't exist. The only ionic compound that exists between sodium and chloride ions are going to be NaCl, which is the 1-to-1 ratio, which is what you need to get a neutral compound with those charges on them. And we can use the same type of logic which compounds have atoms with charges other than +1 and -1. For example, what about a compound that would have a formula MgCl? All right, that would involve magnesium ions, which have a +2 charge. All right, and again, you can figure this out by the position on the periodic table, with chloride ions, which have a -1 charge. All right, so the thing is, if you were to put these in a 1-to-1 ratio, the same type of thing that we do with sodium chloride, you would have this right here. And if you add up all the charges, you'd realize that that is not neutral. Right? So therefore, this compound right here doesn't exist. All right? So how do you get a neutral compound from these ions? We need to have 2 chloride ions for every 1 magnesium ion. All right, that is the ratio that's required to give that neutral compound. So therefore, the only ionic compound between these is going to be MgCl2. All right, there is no such thing as MgCl. In the same idea, there is only NaCl. There is no NaCl2. All right, so there's only one combination for any 2 particular atoms that there's only one compound that can exist. All right, this is going to be a little bit different for covalent compounds. So remember, with covalent compounds, you're not taking ions and combining them. You're taking neutral atoms and you're allowing these neutral atoms to share electrons. All right, so to illustrate this, let's pretend that we have a bucket full of these hydrogen atoms and a bucket full of these oxygen atoms. All right, just a mental exercise. What kind of compounds could we make by trying to combine these? All right, so one combination of these would be one that you're really familiar with. So one of the combinations that you could get would be if you combine 2 hydrogens with an oxygen like this, and you got this compound right here. And the formula for that would be H2O. All right, but another combination you could get is if you took 2 of the oxygens, you combine them in the middle, and then you put a hydrogen on both sides of that, and that would be H2O2. All right, and the thing is, as opposed to the ionic compounds where you only had one possible ratio between the atoms, you actually have 2 possible ratios between the exact same atoms when you do covalent bonding. Or more accurately, I should say that with covalent compounds, you could get 2 or more combinations. The more atoms you have in the molecule, the more possible combinations you could have. All right, so So just realize that's going to be a fundamental difference between these types of compounds. So another difference between ionic and covalent compounds is that with ionic compounds, the simplest representative unit will always have a ratio which is fully simplified, all right, which is not necessarily the simplest ratio between atoms, all right? Whereas with covalent compounds, the simplest representative unit might not be the simplest ratio between atoms, all right? So to give an example of that, let me show you this arrangement of atoms right here. All right, and what would the formula of this arrangement of atoms be? All right, would it be everything that you see here, which is 2 magnesiums and 4 chlorides, or would this be simplified to MgCl2? All right, and the answer is what you're looking at over here is actually just 2 units of this right here. All right, so this right here, this little portion of it would have all of the chemical properties of the original substance. All right, and so therefore, this this compound right here, its formula would be MgCl2. So ionic compounds are always going to have formulas which are the simplest ratio between atoms. You would never have an ionic compound that had a formula like this, because a 2 to 4 ratio could be simplified to a 1 to 2 ratio. All right, things are a little different with covalent compounds. All right, we've talked about this compound before, and we've said that this is the simplest ratio of atoms that are required to make hydrogen peroxide. All right, and so by the definition of formula, which is it's the numbers and types of atoms in the simplest representative atom combination for a compound, well, what's inside of that simplest unit is H2O2. And notice that that is not, even though this is the simplest unit of that compound, it has a ratio of atoms which are not the fully simplified ratio. So, in contrast, covalent compounds can have formulas that are not the simplest ratio between atoms. All right. So sometimes they are the simplest ratio. For example, if we have water, which is this right here, its formula is H2O. All right. And in this case, this right here, what's inside of this arrangement right here, that is the simplest unit of a water molecule. But if you count up the atoms, it happens to be the simplest ratio between atoms, all right? But if you do here, which is the simplest unit of hydrogen peroxide, and you count up those atoms, well, it doesn't give you something which is a simplest ratio between atoms, all right? A last difference is that in covalent compounds, sometimes you can have compounds that have 2 different compounds that happen to have the exact same formula, all right? And the name for those types of compounds are isomers. All right. For example, you've probably heard of glucose before, but there's also this other type of sugar that you might have heard of, which is called fructose. All right. Both of these have the exact same chemical formula, C6H12O6. All right. And that's because they have the same number of atoms. It's just that they're arranged in slightly different ways. All right. So a really simple example of this. If I were to show you this formula right here, C2H6O, and ask you to try to draw a Lewis structure for this compound, some of you might draw this structure right here, but some of you might have decided to put the oxygen between the carbons and come up with this formula right here. All right, both of these compounds exist. All right, they are completely different compounds. They have different physical and chemical properties. All right, one of them's got a higher boiling point than the other. All right, but they share one thing in common. All right, they would have the exact same number of carbons, hydrogens, and oxygens within that simplest unit. All right, so the names of those is isomers. Right, and you don't have that with ionic compounds.